Hello and welcome to our geodetic tutorial. My name is Janine Hilden. I'm an application engineer at Math2Market, and in the following video I will show you how to use the 3D electrochemical mechanical battery simulation tool. I will start with the scientific background. A common observation for battery electrodes is that their active material contract and expand upon charging. This change in volume influences the microstructure of the cell stack, which in turn impacts a range of performance parameters. Since direct observation of these microstructural changes with operandi experiments is challenging and time-intensive, we developed a simulation tool to create this knowledge out of real or artificial generated 3D electrodes. The tool is called Batterydict Degradation and new in Geodetic 2023. This video is the third and last video in the small series of videos on how to create a battery from bimodal electrodes and run a degradation simulation on it. Degradation allows to study mechanical stresses and strains due to deformations of the active materials in the battery cell from a previously run charging or discharging simulation. Let's start with creating a digital battery structure. For this, we will use the two electrodes generated in the previous videos. Open the Batterydict section by selecting Predict and then Batterydict. Select Design Battery and click Edit. Now just click on Browse, and for the anode I select the bimodal anode structure generated in the second video. And then the bimodal cathode structure from the first video. The size and resolution of the two electrode structures match, so we have two green dots here. Otherwise, they would be yellow. Click OK and Run to build a battery consisting of two electrodes, current collectors and a separator. The next step is to define the materials with their mechanical properties. Click on the icon here to open the Constituent Material selector. It is important to choose materials where mechanical properties are available in the database. You can add your own materials with their according properties if needed. For the anode current collector, we select copper. Anode active material 1 and 2 are both graphite. Instead, we could of course also use different materials, for example silicon. For the binder, select PVDF, binder and carbon black. The separator will be polypropylene. For the two cathode active materials, we choose NMC 333. For the cathode binder, select again PVDF, and for the cathode current collector, choose aluminum. Now set the right material law for the mechanical properties. For all active materials, meaning for the two graphite and the two NMC materials, select lithium intercalation. This sets a UMAT, which we can check by clicking on this button here. Unfold the mechanical properties and we can see the two material laws. The option elastic is isotropic and the lithium intercalation, which we chose, is UMAT. When we unfold parameters, we can see the values used. These values here correspond to the Young's modulus, the Poisson ratio, and the concentration expansion coefficient. They are very important for the degradation simulation later on. The measurement was done by Nils Wenzler and Raphael Zahn from the ETH in Zurich. Find the corresponding publication in the video description below. Finally, click Run to apply the materials to your structure. Next, we perform a charging simulation, which will later be used as an input for the degradation simulation. Select Charge Battery from the pull-down menu and click Edit. Here, we cannot edit the mechanical properties, which is why it is important to set the materials up correctly beforehand. But the electrolyte properties can still be changed to match the properties of your electrolyte, or just select the predefined electrolyte from the geodetic database. Make sure that the current collectors also have current collector material law on the right. For copper and aluminum, it is true automatically. Move on to the experiment tab. Since we want to perform a degradation simulation while charging, select Charge Battery Cell. This means delithiating the cathode and lithiating the anode. We will charge the battery with a charge rate of 1 and start with a cell state of charge of 30% and charge until 70% state of charge is reached. The solver settings can stay as they are. Now click OK and run. For me, the simulation took about 15 hours on 16 cores. In the result, we can view the charging curve, the overpotentials, and the lithium concentration in a table, plot, or in 3D result fields. We now go on with the degradation simulation. So select Degradation from the pull-down menu and click Edit. Since we have already taken care of the material setup, we don't need to change anything else in the Constituent Materials tab. Move to the Experiment tab. Here, browse for the charge battery result file from the previous simulation. Automatically, the first and the last result field are loaded as initial and final cap file. Instead, we could also choose an intermediate result file in between, but we keep the selection. We simulate the degradation with free expansion for all 3 directions, meaning that the material is allowed to expand. If you have a battery cell that cannot expand at all, you can choose Confined. To also have intermediate results of the degradation simulation, set the number of steps to 5. Set the boundary conditions to symmetric, because neither of our 2 electrodes is periodic. Leave the solver settings at their default values. Also, we will not change anything in the Output tab. The deformed geometry will be saved for each step, containing the current displacements. To find out the loading for each voxel in each step, the results for von Mises stress and strain can be loaded. Now just click OK and run. The simulation took about 2.5 hours on 16 cores. Here we find the results of the average strain and stress tensors, as well as the average von Mises and hydrostatic strain and stress for each computation step. From the Strain Stress Visualization tab, we can load the resulting structure and strain stress fields after expansion. For example, select the last step, here 5. Then for the deformed solution file, click Load. Here uncheck Structure and move to the Volume Field tab. By default, the strain component XX is selected for visualization. We can also visualize the stress, so just select the von Mises stress from the pull-down menu. I will exemplarily analyze the results for the graphite anode. For this, first we define for which material we want to visualize the stress. Here, uncheck all materials except for graphite, binder, and the separator. To get a precise view, we adapt the color map from percentiles to manual and adjust the sliders. Observe how the stress is higher in the special vicinity of the separator. During charging, lithium ions move from the NMC cathode through the separator into the graphite anode. So apparently, the stress is diffusion-induced and depends on the lithium concentration in the active material, which I can show you by visualizing the results from the charging simulation and the degradation simulation side by side. Observe the correlation of lithium concentration and stress in the graphite particles. This is the end of the last video tutorial in this series. I showed you how to simulate volumetric changes during lithium intercalation in a battery electrode in DEODIC 2023. In the first 2 videos, learn how to generate electrodes with bimodal particle distributions of the active material. If you found this tutorial helpful, please check out our Math the Market channel for more DEODIC videos. Goodbye!